Right.
And we're recording, everybody, and we'll stop recording at the point of the questions as our usual practice.
Okay, can everybody see that?
You can see it, it's
Oh,
not
wait.
green.
Just a second. Just a second. I just did this yesterday. I mean, is this an okay format, or do I need to go completely full screen?
I mean, I think we can see it, but it might be better if you can, you know.
Go to slideshow mode, or?
Yes. I've suddenly lost my mind here. Hang on.
Get with
Oh, it's at the bottom down here. Yes. There we go. How's that?
Perfect.
Great. Okay. So first, thank you for those kind words, Pat, and thank you for the opportunity to speak at this seminar. First of all, I want to apologize for the long title. After I submitted it, I said, oh my gosh, what was I thinking? But it is what it is, and it does sort of summarize the whole talk. And also, I want to thank my co-authors. This has truly been a group effort, and I am merely the spokesperson for much of this work. So, okay, so by outline, I'm going to quickly go through some background material and introduction. Some of you will find this very simple-minded, but I'm hoping that there's several people in attendance, so this will not be so introductory. And then talk about some experiments that we did. The earliest experience we did in negative triangularity and D3D, and then move into some more recent ones where we did a shape change and investigated the H mode threshold of negative triangularity. Some additional reactor-relevant observations, and then I will summarize. Okay, so here's the easy stuff. High fusion gain implies high pressure and confinement. You know, this is the old NT tau we know so well, which can also be written as beta times tau, where of course tau is the energy confinement time and beta is the pressure ratio to the magnetic field pressure. And a Tokamak fusion reactor will require a normalized beta greater than or equal to 3. So this is the so-called Troyon limit. And confinement factor, which is the normalized confinement to the, in this case, the 98Y2 scaling law, greater than 1. And this comes from, for example, recent presentation by Mickey Wade shown down here. And a contender for a fusion pilot plant will need to achieve both simultaneously. In other words, you need high beta and H. So fusion reactor requirements dictate high confinement. And shown here are two examples from D3D of, on the left, a high confinement or H mode plasma, and on the right, a typical low confinement or L mode discharge. So on the right, excuse me, on the left, the H mode discharge has up to 10 megawatts of heating, and it achieves normalized beta in excess or at 3 with an H factor through higher than 1 through most of the discharge. And it has this edge phenomenon known as ELMs, as indicated by the spectroscopic measurements of the D alpha line, shown in this bottom trace. On the right is the L mode discharge with, again, 10 megawatts of heating, but because it's L mode, the power that goes in comes out much faster. It cannot achieve high normalized pressure, so the beta N stays at 1 or below, and the confinement factor stays below 1. And it does not have edge localized mode. So in general, meaningful beta N and H are only achieved in H mode discharges. And this, again, this is a D3D example, but this is the general fact. One thing about H modes is they have a somewhat undesirable feature. And I say mostly because it's also a sort of a pressure relief in some sense, but these edge localized modes are an instability that develops in the steep gradient region at the H mode plasma. And shown here is the same discharge I showed in the previous slide, showing the H mode transition when the neutral beam power reaches a certain level, the density goes up. More importantly, the edge density and temperature go up, so you have a increasing pedestal pressure. And at some point, the edge localized modes start, and they represent power lost out of the plasma. The power that would be injected by ELMs in a reactor is potentially damaging to walls. And if you want to read the horror stories for the ITER device, you should read Alberto Luarte's Nuclear Fusion, which discusses what could happen there and how they plan to mitigate it. But right now, current research seeks ELM-free or at least ELM-mitigated scenarios to possibly, as candidates for future fusion devices. And just list here examples of ELM-free operating regimes are for example, the quiescent H mode or QH mode, sort of regular H modes with this thing called RMP, which is resonant magnetic perturbation. These are edge 3D fields applied that affect the edge and prevent ELMs, or at least mitigate them. And then there's the intermediate mode or I mode, which has edge pressures that don't quite reach the H mode, the ELMing threshold. And what I'm going to talk about today, negative triangularity. So all that is an introduction to this introductory page, which is what I'm going to talk about today is negative triangularity discharges on D3D that have exhibited characteristics of high performance tokamaks with normalized betas and approaching 3 and confinement factors of up to 1 to 1.3. And shown on the right here is a plot from a database of negative triangularity shots. This is confinement factor versus beta N for, again, a host of time slices in these discharges. And it shows that these discharges simultaneously attain high beta N with high confinement H factors. And what I'll be talking about is two shapes. On the left is the, well, I'll talk about these. So all these discharges retain a modest edge pressure and are robustly ELM-free. And what I'm going to conclude with is that many features of this scenario are in line with the needs of a tokamak-based fusion reactor, and it offers a solution to the core edge integration problem for fusion reactors. Okay, so again, more introductory material for the uninitiated. Negative triangularity is a plasma shape where the elongation is on the large major radius side of the plasma, making this inverted D figure. And this is opposite to the more traditional D-shaped positive triangularity discharges that are the most common, of course, and in many variations in current fusion research. And this also is an opportunity for me to bring up that throughout this talk, with a few exceptions, I have this color convention that blue will be negative triangularity data will be shown in blue, and the positive triangularity for comparison will be shown in red. And again, for the uninitiated, these triangularity, this quantity delta, it comes from this parametric plasma shape equations, which can fit these kind of shapes. And so the delta is the triangularity. High values like 0.8 to 1 make a very triangular cross section. Lower values make a more softer D shape. And then there's also this quantity kappa, which I'll be mentioning as well, is the elongation. And for those of you that have Macintoshes or Mac operating system, there's a utility in the applications folder called Grapher, and you can actually plot very simply. This is how these pictures were made using this simple equation. So little tip there. Okay, so now to go on to talking about some data, and with the symmetric interwall limited negative triangularity discharges. At first, as I've shown actually many times to those that have seen me talk before, this research on DIII-D was motivated by and builds on results from the TCV Tokamak in Switzerland, which are the original ones to investigate negative triangularity. And shown here is a plot of diffusivity versus a inverse collisionality. And for a set of discharges where they changed the triangularity of from strongly positive values to negative values, and they saw this factor of 2 roughly improvement in transport, in confinement, as they moved from positive to negative triangularity. And for reference, on this collisionality scale, D3 falls between 1 and 2, but ITER and other next step devices will fall between 4 and 5. So you can see how this important difference in confinement could be important for next step devices. And gyrokinetic calculations predict turbulence reduction as triangularity progresses from positive and negative values. Shown here on the left is a plot from a paper by Greg Rewalt, 1982. And at this time, in the originally Tokamak's course were circular, but in the mid to late 70s on into the early 80s, came to realize that shaping the plasma in something other than a circle may have benefits, in particular with MHD stability. So there is a number of papers from this time period that investigated not only MHD stability, but also turbulence. And this is shown here that this is growth rate versus triangularity. And back then it was more commonly referred to as inverse D and normal D. And you can see that there's a substantial improvement in growth rate of turbulent modes as you go from positive to negative. So this was recognized early on. And then in more recent work, this is from Alessandro Marinoni's 2009 paper. This is a plot of mixing length or heat flux calculations using the mixing length estimate. And it's the y-axis is the triangularity and the elongation is the y-axis, and you can clearly see the reduction in heat flux predicted from this study as you go from positive triangularity to negative triangularity. So as Alessandro points out in that paper, the reason why you get this improved transport in negative triangularity is the weakening effect of the shape on the trapped electron mode by modifying the toroidal precession of trapped electrons. And we've could come up with this heuristic explanation for, so if you look at the trapped particle orbits for electrons in positive triangularity, the trapped electron is mostly in the bad curvature region, whereas the negative triangularity, the same trapped electron spends a portion of its time in the good curvature region, and this is what's basically weakening the TEM mode. So the shape fundamentally changes the way the turbulence contributes to transport. Okay, so now to the experiment. So back in, actually this is 2016, a symmetric, shown on the left is a symmetric, up-down symmetric, negative triangular shape that was developed for D3D. And then on the right, in red, is a matching shape developed to compare to in the traditional positive triangularity. So the important numbers are a negative triangularity of -0.4 and a modest elongation of 1.3. All these discharges were done at a toroidal field of 2 Tesla, anomaly 1 megamp, and had up to 14 megawatts of neutral beam heating power and 3 megawatts of ECH. And an important thing to note for these discharges that like this discharge is designed to ride on the inner wall of the Tokamak. And this was necessary because the outer wall of D3D, since this shape was not intended for D3D, is not designed for heat flux. So if you made diverted shapes here, where that's where most of the power would come out, the wall could not take the power. So so by limiting on the inner wall, that means most of the power will deposit there, and the inner wall is designed for very high heat flux up in excess of 15 to 20 megawatts. So this will be important in later part of the shape discussion. Okay, now some data. So so we did these experiments on D3D to compare the two. So this is a comparison, 2 shots exactly the same heating power with neutral beams and ECH. We managed to get the density the same, but we noticed, well, but right away from the profiles, we see that shown here on the right, the electron temperature is higher and the ion temperature is higher in negative triangularity with otherwise matched conditions, indicating improved confinement for ions and electrons both. And simultaneously, we measure reduced fluctuation levels when we compare the two. So shown on the left is beam emission density fluctuation data from beam emission spectroscopy. This is at with the radius. This is not here. Anyway, somewhere around row of points. Oh, I'm sorry. I did this before. This is a profile of temperature of density fluctuations, fluctuation amplitude versus radius, showing significantly lower density fluctuations in negative triangularity. And similarly, here's the profile of electron temperature fluctuations from the correlation ECE diagnostic, again with a 10%, 10% reduction measured across the radius there. And so both these are measured at the outer midplane. And so the reduced turbulent transport, of course, manifests itself in improved global confinement. So here's on the right plots of electron and ion diffusivity as a function of radius. And you can see in the confinement zone that significant reduction in chi-e and chi-I. And again, these are matched discharges of the same heating power and density. And so from power balance, you can see these 20% improvements, both in the stored energy and the confinement time. And then we continued adding power to these discharges and seeing continued improved confinement. Shown here is time history from 2 discharges. Both of these are negative triangularity. And they actually attain a respectable normalized beta of 2.7, H factors that of 1.2, all without forming edge localized modes. And as I pointed out earlier, in the D3D discharges, D3D discharges and tokamaks in general running in L mode do not attain beta normal levels above, say, 1.5, and certainly not high confinement factor. So this was unprecedented levels. And it's notable that when you ramp up the power, we didn't encounter any disruptive MHT. These plasmas, actually, the plasma in blue was terminated by administrative limits because, again, there was concern still, even though we were inner wall limited, of heating up the outer wall. And you can see that in the subsequent shot, we actually got that extended so that wasn't shut off early. And another comment to make here is initially we set out to do this experiment as a pure transport experiment. So we were just going to put in a little bit of power, both ECH dominant and neutral beam dominant, but it wasn't expected we could put in very much power. It was it was believed that these would disrupt, these backward D plasmas would disrupt before we got to normalized beta of 2. It was based on just this notion that the positive triangularity is supposed to be very good for MHT stability at high beta. Well, the negative triangularity must be bad. And but early on, we were doing the experiment and we were inching up the power as we were allowed, and we kept seeing that we could go higher and higher without it disrupting. And in the meantime, the beta was improving, and the as you can see, also the H factor improves with increased power as well. So this, was sort of an accident, and this doesn't always come out in discussions of this, but this was an unexpected thing when we first did it. Pleasant surprise. So finally, a more recent result, excuse me, is in 2019, we finally got some time. So most D3D discharges invoke error field correction to correct for inaccuracies in the shaping coils and so forth that can limit performance. This has been done for positive triangularity, but because the shape is so radically different, it was known that it was believed and verified that the error field correction would be significantly different for negative triangularity, and that is shown here. The red is the positive triangularity case, which the center is here, and this is actually a quite a different correction that you have to apply to negative triangularity to null out the error fields. And the result of this is that we got a 5% improvement in performance, and actually this is where we finally are sneaking up on this magic beta N of 3. With, and you notice here, we go up to, in this shot, 13 megawatts of neutral beam power, plus we have some ECH, and we still have no H mode transition and no ELMs. Okay, so, excuse me. Now moving on to diverted negative triangularity discharges. So we had explored of course, these symmetric discharges, they were stubbornly remaining in H mode. So it was believed that if we could make a diverted version of at least half the discharge in negative triangularity, we could investigate negative triangularity and try to get, and make it go into H mode so we could study that. So we were sort of being greedy. We had already this good performance with symmetric shape, but it was thought that if you add the good confinement of negative triangularity with an H mode pedestal and edge, then it would just get super H mode confinement. So this shape was shown on the right here was developed with, again, upper negative triangularity of roughly 0.4, but a neutral or near zero lower triangularity that allowed a diverted shape down here, an open diverter. And this shelf here can take as much power as the inner core. So again, the goal here was to try to get an H mode, look at ELM behavior, and evaluate heat flux widths. And so here are shown on the right the results of that effort. So these are time histories, again, heating power, density, beta N, and so forth. And so we were able to get the same performance, high beta N with sufficient power. And then again, we went up to 13, 14 megawatts of auxiliary heating power. H factors, again, at 1, not quite as good as the symmetric negative triangularity. And this is roughly attributed to the lower average triangularity, but no H mode transmission. And again, we fed this thing up to 14 megawatts of auxiliary heating power, which is from the scaling law 5 to 6 times lower the L to H transition power. So this was kind of a bummer, but we did have a one case that did actually transition to H mode, and I wasn't necessarily going to bring this up, but we actually didn't know about this until a week after they ran the experiment. So that's a little interesting thing that you have to understand, that when you're running an experiment at DIII-D is an exercise in controlled chaos. And this is just something we missed. But in subsequently, in looking over the data, we noticed a mode that looks like it had developed ELMs, excuse me, a shot. And that is shown here. And so what had happened is this shot 180520 had a unintentional glitch in the plasma control system, such that one of the coils was turned off that is affecting the shape. And so we had this relaxation of the upper triangularity. And when this shape control error occurred, we ended up getting a immediate transition to H mode. And shown here, you can see the density jumping up, which is the sign. So again, in hindsight, we saw this, and you can see here the ELMs as they started forming, clearly indicating H mode. But notably, beta normal didn't go up that much, and neither did the H factor. So this was really a only minor improvement in performance for these shots. Yeah, I didn't know. This is in these discharges, the grad B drift is in the favorable direction. So of course, that's again why we were so surprised we didn't get the transition. So here are shown are the profiles from these discharges. And so yeah, so the one that went into H mode, we ended up getting the steep density, which is more typical of H modes. Interestingly, the temperature profile shown in this lower box, TE versus rho, looked very much the same. And in particular, they had the same sort of pressure profile out here. So if you let me digress for a minute, on Tokamak's, the H mode is characterized by these increased, these pedestals at the edge, this increased pressure due to the barrier that forms very near the last closed flux surface. And shown here on the right are profiles of density and temperature out in this outer region for typical shots on DIII-D. So the magenta one is a standard H mode. It's not the matched one. It's just a random H mode. And again, you can see the very high density and the steep density profile, and also the high electron temperature at the edge. And then shown in red is again sort of a not related to negative triangularity, but a standard typical L mode discharge. So both of these are at 4 megawatts, all three of these cases actually. So shown in the middle in blue is the one of these L mode edge negative triangularity shots, except for it actually has this small T pedestal at the edge. And this, if you go through the numbers and integrate the profiles, you find out, you get a lot of leverage in stored energy by having a little pedestal. And so this higher pedestal at the edge contributes 20 to 30% increase in stored energy. And this little, again, steep temperature region at the edge was also observed on the TCV Tokamak and talked about briefly in this paper by Sauter. But we currently don't understand this. This is actually something that we're just starting to look into, is why even though these are inherently L mode-like discharges, they have this sort of I'm intermediate mode-like profile. And I note that there's no weakly coherent mode that characterizes the I mode. And so it's got to be something different. Anyway, back to our H mode discharge. So ballooning stability study was done to look at the limiting effects in these diverted negative triangular discharge for both the strong and relaxed shape case. And this is work by Sam Terelma, who has just recently submitted a paper to PPCF. And shown here are the typical plots you make in these stability studies. This is normalized pressure gradient versus radius, and this is the radius very close to the edge in the steep gradient region. And if you, for L mode profiles, you get this stability picture. So for both the strongly the strongly negative triangularity and the relaxed triangularity cases, there is no second stability axis. And of course, this is what allows an H mode pedestal to develop, is the access to second stability there. But if you change to the actual pressure profile observed in the experiment, then for the case of the relaxed triangularity, it opens up this stability boundary. So you have access now to second stability. So this is a developing picture of what's going on here. So for strong negative triangularity, these n=infinity modes limit gradients. But for the relaxed shape, the bootstrap current opens up this second stability. And so the picture we have of the negative triangularity remaining in L mode is that it breaks this virtual cycle that we come to know for H mode formation, is where the E cross B shear suppresses turbulence, it allows the pressure gradients to rise, which increases the E cross B shear and so forth. This bootstraps, it's probably not a good word, that this cycle that makes this happen. The shape and the ballooning stability breaks this cycle, and this is again what makes the negative triangularity robustly with an L mode edge. Okay, so moving on to some other aspects of this diverted shape. Like I said, we wanted to measure heat fluxes, and this is work by Filippo Scotti, measurements with the infrared camera. So this measures parallel heat flux versus radius. So we're looking at a portion of this lower divertor with the strike point. And so this is the width of the lamp. This is how you measure the scrape off layer power fall off. And you can see that for the, again, this is where the color convention went out the window, because you can't get everybody on board. But for the case with the strong triangularity, which remained in L mode, the heat flux width is significantly wider than the one that went into H mode. And so this bodes well for maintaining a reasonable heat flux width for negative triangularity if you were to go to serious devices. And similarly, we also measured, and this is something I hadn't really talked about yet, but what a key thing about, of course, reactors is pure with the H mode transport barrier. You can have problems with impurities getting retained and sucked in to the plasma. So in these discharges, there were injections both of aluminum shown here on the left and fluorine shown on the right. And so this is the characteristic particle confinement time derived from the fits of these. And these particle confinement times for these L mode cases are on the same order as the regular particle confinement. So whereas standard H mode plasmas typically measure particle confinements 2 to 4 times the energy confinement time. So this implies impurity retention will be less of a problem than negative triangularity, which is, again, to be expected if you don't have this transport barrier at the edge. Okay, so just a few more what I call reactor-relevant observations. Negative triangularity in these symmetric discharges, we looked at the bootstrap current. It was actually noted in these high power discharges that we were consuming very little of the toroidal flux that drives current at the end of these discharges. So it was indicating just from control room observations that we were getting some bootstrap current. And so we did a comparison and showed here on the right is the actual measurement from this NV loop analysis that's been developed. And the numbers that it comes up with, the bootstrap current is, bootstrap fraction is on the order of 25% for this negative triangularity case when we compare to the positive triangularity. And this is a positive triangularity that went into H mode, and therefore it has the steep pressure gradients at the edge, which give you this edge pressure. And so you see that these negative triangularity is producing comparable or better bootstrap current, again, which bodes well for negative triangularity as a non-inductive case. And part of the reason that the trap particle fraction is actually always higher and negative triangularity due to the geometric, this geometry of the shape. So, okay, and getting close to, I think just have a few more slides here. So here is a comparison of negative triangularity of our database with other ELM-free shots on D3D. And I already mentioned what some of these are, quiescent H mode, H modes with ELM suppression by RMP, and I modes. And you can see that in this plot of normalized beta versus confinement factor that negative triangularity does very well when compared to these, with particularly with not as good as quiescent H mode, but certainly better than I mode and EDAH mode, for example. And this, by the way, is from a paper by Carlos Pasadan, where he looks at the various ELM-free cases in D3D. And finally, this is something that really doesn't amend itself to just showing data, but it's something I'd just like to mention about. So in running these negative triangularity discharges, they were initially, of course, a challenge to create due to the radically different shape. But once these were made, they were actually turned out to be very easy to run. And I pointed out earlier the discharges where we saw no MHD modes that developed and caused disruptions. I mean, shown here, I just showed one of our favorite performance figures of stored energy versus power, showing that the negative triangularity does better than either scaling. So you don't have this degradation of confinement with heating power and negative triangularity. But the point more of this slide is that even though so far we sort of ran these discharges when we could, so we didn't have pristine wall conditions. We didn't necessarily have super bad, but we didn't have we never ran after aboronization with those very good wall conditions. And, beginning we didn't have optimized air field correction. But nevertheless, we observed significant beta, good confinement, and again, no MHD problems, no impurity accumulation. In particular, in these high discharges, the neutron rate was quite high, owing to a lack of impurities like carbon or even metals being pulled in, which dilute the deuterium. And of course, all of these, other than that case where the accidental relaxation of shape, we have seen no ELMs in negative triangularity. So any negative triangularity that has retained its shape, we have no experience any ELMs. It's been completely ELM free. Okay, so for the future, like I said in the beginning, we can't make a true diverted, symmetric, negative triangular shape in D3D because of the outer wall not being able to take the power. So there was a proposal put into the FES to armor up the outer wall by adding carbon tiles that are either cooled or beefed up to allow this shape. So this would be a lower single null with the upper not diverted, but again, symmetric negative 0.4 triangularity. And this has actually been approved and is tentatively on the schedule for to be done in FY23. And so, in summary, additional experiments in D3D with negative triangularity confirm the favorable performance, sort of again and again. Especially with these experiments with the upper negative triangularity, the sort of hybrid shape, retain H mode confinement, and we noted this I mode like TE pedestal. And again, just like I said, we have not yet made an ELM when we've maintained the shape. And so this growing database sort of, again, good H factors, reactor-relevant beta, significant bootstrap current, no ELMs, evidence of wider lambda Qs, all point to this being a promising scenario for a reactor. And finally, one of our biggest fans has been Mitsuru Kikuchi, who was so enamored he wrote a paper about building a reactor out of negative triangularity, and shown here is a figure from his paper. And something I haven't pointed out is one of the advantages of negative triangularity is you can put the diverter farther out in major radius. So that alone gives you a larger area than inner to distribute the power, but it also gives you more room and more flexibility for building a diverter out here rather than constraining it up against the inner stack. So with that, I thank you, and thank you for your attention.
All right, thank you very much, Max. I wonder, when you give that talk in Texas, do you reverse the blue and red color coding? Was a thought running through my mind during the talk. But and we already have some hands. So Sergey was first, so go ahead.
Max, I wanted to ask you the following. So
Did you try to inject high Z impurity? And if yes, then what did you find with the confinement or accumulation? When I'm saying high Z, I mean maybe argon, which is pretty high for DIII-D standard.
No, we haven't done that yet. Again, the only things that were done so far are aluminum and fluorine.
Okay, reason I'm asking about high Z because this, along with kind of no need for HMO transition, then potentially in the reactor you can re-radiate all your power virtually from the core, and then this kind of H plasma or diverter will be just obsolete. Okay, and I believe this would be the best solution ever. So therefore, if you find that there is no accumulation of high Z, then that would be absolutely kind of perfect situation. Thank you.
Yeah.
Is that, are you done, Sergey, or?
Yes, yes, I'm done. Thank
All
you.
right, I thought it was, I was such a long speech, I didn't know whether you were done or not. So I think I'm next. So I mean, I've heard your talk a few times, and it's exceedingly interesting. One thing I hadn't caught before was the I mode-like behavior of L mode, and also this charming tau p to tau e ratio. I mean, the question that immediately comes to mind: what's the new star E at the edge?
Oh,
Right, because I mean, you tend to associate particle transport and all with trapped electron modes, right? So what's going on there, right? And in particular, more general question is, can you comment on the, you know, it seems you get an I mode without the so-called weakly coherent mode, whatever that is. I mean, that's another interesting discussion. And what can you say about the structure of the edge turbulence?
yeah. So the first part, I even if I'd calculated it, I guarantee you I wouldn't remember what new star is at the edge. This is, you know, something I would look into for exactly this purpose. But as far as this I mode like edge, the only thing I have done is surveyed many of the diagnostics, of course, including my favorite electron temperature, the ECE, to look for any modes there or lack of modes. And it's mainly it is a lack of mode. I haven't, I will confess, I haven't looked at beam emission spectroscopy data. So I'll maybe hitting George and company up at some point.
We have the relevant criminals here, right?
Yes,
So
yes. So yeah, the short answer is I haven't noted yet any particular edge modes that may be. Of course, you know, the weakly coherent mode is sort of a mode that is preventing the pressure buildup, I think, if I understand that. Whereas in this case, you know, we already have the ballooning stability, which is preventing the pressure buildup at the edge. So you don't, as I see it, you don't need a mode at the edge to limit density or whatever.
yeah, okay, interesting. So next is George.
The attractive features of you know, L mode edge, no ELMs, and so on is interesting. You made a comment somewhere, you didn't discuss much about it, but you mentioned in passing that the negative triangularity sort of broke the feedback loop of E cross B shear, quenches turbulence, which causes pressure gradient. I'm wondering, how robust is that result? If, in other words, if you had high enough heat flux in a negative triangulary system, would it pop into H mode and then all the nice features would be lost?
Yeah, that's a good question. And I see Lexi. One of the thing I wanted to say here is I've washed over a whole thing that Lothar Schmitz has investigated in these discharges. And, you know, I think he recently gave a talk to this, but you should invite him back because it's actually a very nice work that he's done on investigating these edge conditions here. But yeah, I don't know. I think it's an open question. What would happen with higher power, and certainly an area that we, you know, given the opportunity to more experiments, we'd want to explore. So that's really all I can say.
Okay, thanks.
All right. Speaking of the devil, Lothar.
Yeah, so I can mainly comment on the comparison of the lower and higher negative triangularity discharges. So what seems to happen is that if there is a threshold, it's extremely high. So above the 14 megawatts that I would put in, and that's about 6 times the equivalent threshold in a positive triangularity plasma. There is slight differences in the edge profiles. For example, in the diverted discharge, the density gradient tends to be a little bit steeper. So eta I is different. And when you do the linear stability calculations, it turns out that the ITG is more unstable in the positive triangularity discharge than at negative triangularity. So it's a little bit more TM dominated. And the other thing that happens is that the a discharge that doesn't go into H mode, that is diverted negative triangularity, still has LCO-like phenomena. So in other words, you get steepening of the edge density gradient, periodic steepening of the edge density gradient, but because of the lower ballooning limit, it just does not build a pedestal, right? So it goes basically through the LCO cycle that periodically the cross species is increased, but it's not enough to maintain it in a state that the pedestal can really grow and feedback on its own growth.
Mhm.
That's as far as we can tell regarding the edge dynamics.
See, while we have you on the spot, Lothar, can you comment on the edge turbulence, since you were your name was taken in vain there earlier?
Yeah, what I just said is that basically the higher pressure, the higher density gradient makes ITG more stable. So it's typically in a mixed mode regime that you have TEM and ITG at the edge, and it leans more towards TEM in the negative triangularity. In the only speaking about the diverted discharges now, right? So there's an independent effect in the core that Max commented on in terms of the curvature drift, but I'm just talking strictly about the edge here.
But I mean, in some sense, the preferential survival of TEM relative to ITG would tend toward making increasing particle transport relative to heat transport, which is good, right? So
right, that would be desirable, yes. That's right. And then, of course, you could tailor that potentially if you have a handle on the triangularity that it's basically variable shape, then, of course, we may be able to tailor that a little bit more.
Ooh, I like it. All right, Dr. Holland.
Thanks. So yeah, maybe picking up on this thread, but coming at it a little bit different way. Do you have a sense of how much rotation impacts things? I mean, obviously, if this is one rotation seems to help lots of stabilities, but also drives high TI over TE, which plays in all kinds of havocs, both of what modes regulating things, and then also what your power flows are, and how that would extrapolate to a reactor. So.
Right. So yes, no doubt that the rotational shear, which by the way we mostly use co-beams, so there is fair rotation. And matter of fact, it looks like in some cases the momentum confinement is better in native triangularity. So these things are rotating pretty well, and no doubt there is E cross B shear. And actually, this lets me use one of my extra slides. So this is from Alessandro, looked at this effect of rotation shown here on the left. I've squeezed two things on here, but mainly over here on the left. This is modifying the experimental profiles. It does show that if you go to low rotation, you expect a heat flux increase, and so of 30 to 40%, as he shows here. So yes, this could be significant, but in some sense, this isn't a surprise. We see this in positive triangularity. But this is at the top of our list for sure of one of the experiments to do next is to do balanced injection and low rotation and see how confinement changes.
Yeah, I mean, certainly, I think it'd be interesting, obviously from the confinement standpoint, but also from the stability standpoint of, if you think rotation maybe helps, with all, the tearing modes and lots of other things, if that helps shield any of that other stuff, then that's, double bonus.
Right. Yeah. Well, you say double bonus, but yeah, it could be sobering to say the least.
Yep.
Let me ask a follow-on to that. I mean, we talk about intrinsic rotation, but of course, there's people busily out computing intrinsic current drive, which is a particularly interested in the edge. And Lou Wong and also Chris McDivitt's names come to mind. And you were the comment about the better bootstrap, right? The point of intrinsic current drive is a kind of turbulent driven bootstrap current. Have you guys looked into that at all?
I haven't. Yeah, and you're talking about, this is something at the very outer edge in particular.
Right.
Yeah.
That's where it counts. I mean,
Yes. I vaguely remember a conversation with Tim, whose last name Sophus Duke, where he was also interested in this. I don't know if he's had time to think about it more. Yeah, it's a good point.
Okay. Dr. Badger, please.
So Max, I've asked you about this before, but it goes back a ways. So maybe your new understanding or increased simulations have shed some insight on this. But one of the things that happens, you've done these sort of dimensionally matched discharges, same current, same field, but flip the triangularity in the shape. So a natural thing that happens is Q95 changes. And let me make sure I get this right. Positive triangularity is slightly higher Q95. Negative then goes a little bit lower. Is that right?
No, it's see the due to the shape, the average B field is somewhat lower in negative triangularity, so that ends up gosh, I can't even think, giving you higher Q, right?
Is that the case? Okay, then maybe I have it backwards, because I thought maybe when you did the full equilibrium reconstruction, you got lower Q. I guess I was thinking that the direction that Q95 changed in was such that it would be, you might expect better confinement. And but if it actually goes higher, then in a sense there's a double benefit to negative triangularity. So we should find that out. But typically, if all else is equal and you go to lower Q, you might expect Q95. You might expect better confinement. All else being equal, but so maybe I'm misremembering that, but that'd be a good point to follow up on.
No, I mean, that is a fair point, and this has been remarked before, but also in an experiment, I can't remember if they actually published this, but TCV did a similar experiment to what we've done here, except for they deliberately changed the parameters so they to match Q, match the safety factor, and they still found that the negative triangularity was superior to the positive triangularity. So whatever benefits from the improved safety factor are
Further
Not enough
augmented by the negative.
to account for the improvement. So
Okay. And then if there's no other questions, I have a related, I guess it's a comment/question, but I guess is the robustness of this mode to radiative impurities. I guess we probably are going to say we don't know enough about that yet. We haven't really done the experiments, but it seems like they might be very good candidates for that. Has there been any new thinking on how, basically to further improve the reactor attractiveness? Can you, if you have good particle transport, in other words, this low PT over, tau particle over tau energy confinement, good flushing of the impurities, and maybe you can get a radiative diverter or radiative boundary without accumulation.
right, and what you may not be aware of is, Alessandro led this experiment with the diverted, and he actually tried to increase density to the point where the diverter might detach. We didn't puff impurities, but there have been on TCV mixed results from this. They actually, as Stefano Coda reported it at the AAPPS meeting, found harder to detach. This goes against some simulations done by Princeton, which show it should be easier to detach. So no, short answer is we haven't done it yet. It's high on the list of things to look at. Particularly, right, you say in using impurities to help there, knowing that they're not going to be entrained and sucked into the core.
Okay, thanks.
All right, Ramaswar.
Yeah. So do you have any idea of how zonal flows compare in positive and negative triangularity?
Zonal flows?
Yeah.
Not off the top of my head. All I know is, I looked at one point, I thought, if you keep a D3D discharge with positive triangularity in L mode with high power, you always see the geodesic acoustic mode, you see GAMs. And originally I didn't see any GAMs in negative triangularity. So I was thinking, and these are driven by zonal flows. So I thought, well, there's not enough turbulence to drive zonal flows. But and in fact, in looking harder, I have seen, because this is actually showed up at a slightly lower plasma current. I have seen GAMs in negative triangularity very similar to GAMs that show up in positive triangularity. So based on that, I'd say the zonal flows are similar, I guess, from an experimentalist viewpoint.
Let me ask a follow-on there. What's the story on gyrokinetic simulations of negative triangularity?
Okay, I actually have, there it is. So after much labor, Alessandro, he's multi-talented and he can actually do these non-linear runs, which I don't even think about trying to do, has actually done C-gyro calculations for these, using the experimental input for these discharges. And so this is the results here for the case he did. This is negative triangularity and matching positive triangularity. The profiles from one of the experiments with both neutral beam and ECH. So T approximately equal to TI. And the gyro simulations show significantly lower energy flux for negative triangularity compared to positive. I mean, notice the scale is a factor 2 different, and then these are still higher. So, I mean, I think reduced fluctuations and reduced turbulent transport are both experimentally and from any simulations, because we've also at Texas, Gabrielle Merlot, who's actually not at Texas anymore, has shown similar things with gene simulations. Purely show expected reduced energy fluxes.
Well, the cynic would say that's all very good, but you know what's coming. It would be nice to understand why, right? I mean, in the sense, you know, this is the flux goes down. That's good, right? But I mean, it goes down because of linear stability improvement, stronger zonal flow, blah, 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 whatever it is, right? It would be interesting. I mean, he's obviously got the data. Someone should analyze it, right? That would be the gratuitous comment. So,
sure.
And it's also relevant because the power threshold for transition to H mode is so high. I mean, and that depends on the level of zonal flow.
Right.
any other questions? Gyeongjin, go ahead.
Yeah, just one stupid question. So we found positive effects of negative triangularity, which is opposite from conventional one. Then what happens if we have elongation opposite from the conventional one? Sorry for stupid question, just suddenly curious.
Yeah, in this case, you know, if you look at the history, elongating from a circle, you know, the original tokamaks had circular cross sections, and a ton of theoretical and experimental evidence points to that if you stretch it, it gets better. I don't know if, I assume, and I'm not aware, but I assume it would only get worse if you were to squash it and make it less elongated. Certainly from a operational standpoint, you know, one of the benefits of elongation besides MHD stability and turbulent stability is that you get more, you can fit more plasma current in at the same Q. So it's, you know, from a very fundamental standpoint, elongation, which is why spherical tokamaks are also all the rage. So it's, yeah, but it's interesting to think about all the different shapes. You know, negative triangularity had been written off long ago. So it's fun to think that, you know, what if you just tried this, maybe something unexpected. And right now we're pretty certain that the other direction is not the way to go.
Okay, thank you.
Okay, so we won't make a meatloaf out of D3D. That's good. And any further questions? Well, I'll have one more. I mean, since these days you have to speculate on reactors and all, and whenever you come to reactors, immediately at the top of the mind comes disruptions. What's the lowdown for negative triangularity on disruptions?
Well, as Carlos Paz-Soldan presented, it doesn't solve anything necessarily there, other than, you know, I noted that we really haven't experienced any MHD driven disruptions, but there's nothing to prevent any of the normal disruptive elements from, you know, doing their bad stuff on negative triangularity. I think that, you know, that's still largely a plasma control and area that, you know, it is very general in terms of shape. So yeah, but you don't, it's not clear you would get any benefit from negative triangularity in that department.
All right. Anyone else? All right. Let's thank Max again for a stimulating discussion and talk here. It was very interesting. So thank you very much.
Well, thank you for hosting.
Oh, our pleasure.
All right.
Thanks, Max.
Everybody.
See ya.